All right, guys, welcome back. Clark, honey, the spandex suit goes under the business suit, remember? That's Superman in his later years. Okay, guys, we're continuing on acid-base equilibria. Okay, so we talked about strong acids and strong bases last lesson. You guys remember that's complete dissociation. Now we're going to work a little bit more with weak acids and weak bases. So this is a typical thing that you need to be able to do is calculate the pH. You remember the pH tells you the acidity level from the Ka. And you remember the Ka tells you how strong or weak an acid is. So this says calculate the pH, and notice it's in purple, so you guys should write it down. It's good to have a representative problem to look back on your notes. Calculate the pH of a 0.3 molar solution of acetic acid. You guys remember acetic acid is essentially your vinegar. And you guys can tell, you guys should just be able to look at that and tell it's an acid. You guys see it's got the hydrogen there, okay? And what do acids do? They tend to give up the hydrogen. So if you should be able to even actually write this chemical equation just from this right here. You put acetic acid if it's in water, because that's what vinegar is. It's acetic acid in water. And then you can see the acid would give up a hydrogen, can give up a hydrogen to the water and form the hydronium ion, or H+ ion. And then you guys see this is acetate, which is the conjugate base of this. You guys see why it's called a base? Because just as the acetic acid can give up a hydrogen to the water, in the reverse, you realize this is a reversible reaction. The hydronium ion can give back the hydrogen to the acetate, and therefore it acts as a base, right? It takes, you remember, acids give hydrogen ions, bases take hydrogen ions. And so, what do we know from this point? You guys remember acetic acid, it's not one of those seven. If you remember the seven, so therefore it's a weak acid. So which side of the reversible reaction is favored? It's the left side. You guys remember, acetic acid prefers to be associated. It holds on to that hydrogen much more strongly than a strong acid would do, which gives it up. So, you can look up the Ka for acetic acid. It's 1.8 times 10 to the negative 5. Once again, what does that tell you? The fact that it's so small tells you it's a weak acid, right? It doesn't dissociate very much. So we need to get the pH, okay? So you got the equilibrium constant expression. You guys see? You're right. You guys, when that expression comes, it's the ratio of products to reactants. Notice it's missing the water. So this is our Ka expression right here, okay? So we already know this is where it's different. We already know our Ka value. What are we trying to get? Is the pH. And you guys got to remember, what is pH? pH is the negative log of the hydrogen ion concentration. Remember, hydrogen ion is the same thing as hydronium. So basically, we're kind of going the reverse. Whereas before, we would figure out these equilibrium values and then plug them into the expression to get the Ka. Here we have the Ka, and we ultimately want to get the pH, and I can get the pH if I get the hydrogen ion concentration. So basically, I want this value. So we got ice. You guys remember, when in doubt, use ice. So remember, we have our acid dissociates into the hydronium ion and then the acetate ion. You remember, initially it was 0.3. This is what we got from our initial problem. It was 0.3 molar. So initially, before it dissociates, this is 0, 0. Once again, we don't know how much dissociates. So what do we call it? Don't we call it X? So X amount of this reacts. It's a 1-to-1 ratio if you look from the equation. So for every X that reacts here, X is formed and X is formed. Notice these are both X because they have the same coefficient. Then lastly, so this one's pretty easy. So at equilibrium, it's going to be initial minus whatever was added. So it's 0 plus X is X, 0 plus X is X. And on this one, you'd say, I think it's 0.30 minus X. But you guys got to remember, it's a weak acid. And therefore, we only expect very little of it to dissociate, so much so that usually what we'll do is we'll just assume that this number is so small relative to this that for all practical purposes we'd say it's 0, and then we would say you end up with the same, essentially the same concentration that you started with, and that's what that's saying right here. Oh, where's my clicker? Sorry guys, I'm missing my my laser pointer. There's my laser pointer. Okay. All right. So now, you guys, right? We have 1.8 times 10. You guys see what we did? We just took these values and plugged them into the equilibrium expression. So it's X times X, which is X squared over 0.30. Right? And then it's just a matter of solving for X. So I multiply both sides by 0.30, and that's X squared to get then I get the square root of that. And so I got X is 2.3 times 10 to the negative 3. You guys got to remember, what was X? X was the hydronium and the acetate, so that is my hydronium ion concentration. So then, as you guys might expect, if this is my hydrogen or hydronium ion concentration, wouldn't I just take this value and plug it in there to get my pH? So you guys should know the pH formula is pH is equal to negative log. It's the negative log of the hydrogen ion concentration. So that's what I do, I put it in there. So this is pretty simple. I put 2.3 exp negative 3 in my calculator. I press the log button. I change the sign. I get 2.64. Why should that look pretty reasonable? Well, you guys know it's an acid, so we better get a number less than 7. This seems to fit. It seems pretty reasonable. I'm hoping when you guys come up with an answer, you guys assess it to think, is it at least reasonable based on my understanding of it? Okay, now you guys, weak bases. So that was an example of weak acid, weak bases. So you guys remember what bases do? They accept hydrogen ions. You guys should know a typical weak base is ammonia. You guys remember that's the main ingredient in Windex. But you guys can see from the Arrhenius, remember the original definition of a base was that it gives OH minus ions. But if you look at that, you would look at ammonia, you wouldn't recognize it as a base based on Arrhenius's definition. That's why Bronsted-Lowry's definition is better. They say they define a base as something that takes hydrogen ions. So that's what's happening here. So you put ammonia in water, just like in Windex, and what's going to happen, this acts as a base. You guys remember it's got a lone pair of electrons. That's going to attract one of those hydrogen ions, so it's actually going to attach to it and form NH4+. And then you guys see, right, the water in this case acts as an acid, and then what's the result? You do end up with hydroxide ions in solution, and that's what makes it a base. Okay, so this would be this is showing the how a base would act in water, right? Just much like with the acid. Okay, and so you guys, we can do a KB. You guys, right? So it's the equilibrium expression for a base. Once again, it's the products over the reactants. That's what it is. So it's KB equals the products, which is the right. That was like your NH4+. That was your OH minus. If you look back on the previous slide, and this was over your base. Okay, and it's KB for a base. And so here's some typical KBs, and you guys can see these numbers. I don't know if you guys can see it: 10 to the negative 5, 10 to the negative 9, 10 to the negative 8. They're all really low values, indicating they are weak bases. They only partially. Meaning they remember strong bases completely ionize, weak bases only partially. So here's a typical question: what's the pH of a 0.15 molar solution of ammonia? Okay, let's say it kind of like we got our Windex solution. So this is we should be able to write this equation just from this. We know ammonia is a base because I've just told you over and over it's a base. You put it in water, what's it going to do? It's going to accept a hydrogen ion, form NH4+ and OH minus, right? And it's the increase in the OH minus ions that ultimately makes it a base. So we got our KB expression, products over reactants. This is all stuff we should be doing. This is, we looked this up. The KB for ammonia is 1.8 times 10 to the negative 5. So if I want to get the pH, you guys are thinking, man, to get the pH, don't I need that hydrogen ion concentration? And you're like, but we're not looking at hydrogen ions here when we're talking about a base. So here we'll kind of show you where we're going with this. So it was a 0.15 molar ammonia solution. We start right before dissociation or ionization. Those are both 0. And then at equilibrium, once again, we don't know how much it's going to react. What are we going to say? Minus X, and then that could be X, and that's going to be X. And once again, it's a weak base, so we only expect very little of it to ionize. So for the most part, we leave it as 0.15. This is typical with weak acids and bases. And so then we're going to take these values and plug it into our equilibrium expression, right? So the X squared on top, 0.15. And then obviously I can solve for X. Multiplying that, then I'm going to take the square root, and I'm going to get X is 1.6 times 10 to the negative 3. Now I want to go back. So what is that X value? Well, you know what's going to help? You remember, whenever we're dealing with acids and bases, what do we care about? H pluses and OH minuses. Always focus on that. So our OH, so we just figured out what our OH minus concentration is. And here's the easiest way to do this. So our OH minus concentration is the X value, right? That's our. Now what you could do at this point is you could get the POH. Remember the POH? It's the same thing. pH is negative log of H plus. Well, the POH is the negative log of the OH minus, so I get the negative log of that. And so my POH is 2.80, and if you guys remember from our last lesson, the pH remember, you guys should have this written down too. This is a good pH plus POH is equal to 14. So what we do is just go 14 minus 2.8, and we get 11.2. That will be my pH. And you guys, why should that sound reasonable? You guys remember we're dealing with ammonia. Remember, it's a base, so I would expect it to have a pH larger than 7, indicating it's a base. Okay, so we've got Ka and Kb. You guys, here's some, notice nitric acid's a strong acid. What are we seeing here? Oh, this is what I wanted you to see. What do you notice about the Ka and Kb? Look, for example, we have HF, which is a weak acid. You can tell it's a weak acid, it's got a low Ka. You guys see how this is the conjugate base? And the conjugate base, and then has a Kb associated with it, right? And that's showing you the likelihood of it to acquire hydrogen ions, right? You guys can see if a hydrogen goes with F, it goes back to HF. If hydrogen goes with acetate, it goes back to acetic acid. If another hydrogen comes with bicarbonate ion, it goes back to carbonic acid. So every acid has a Ka, and its conjugate base would have a accompanying Kb. But now if you notice this, if you look at these values, obviously you guys can see the higher the Ka value, the lower the Kb value, right? And then and these are really low Kb values. The lower the Kb value, the lower the Ka value, the higher the Kb value. But if you multiply these together, what do you guys think you would get? You could punch it in your calculator. If you take Ka and you multiply by Kb, you know what you're going to get? Should be a number that looks familiar to you. You're going to get Kw. And what is that value? Remember what that value is? 1.0 times 10 to the negative 14. So that's good to know. So what that tells you is, if you know Ka, you could get Kb just by taking this and dividing by Ka. And if you know Kb, you can get Ka by dividing it. So when you know one, you know the other. He said I decided to eat lunch at my desk. This guy's cute. All right, you guys, last concept. Okay, so we're going to be talking about some things here. The effect of cations and anions. You guys know cations are positive ions, anions are negative ions. So we want to see what kind of effect might these have on solutions. So here's the question I'm posing. Will adding a salt affect the pH of a solution? Now I'm going to remind you guys, in any solution, when we talk about a solution, it's a water-based solution. And remember what water does, it partially ionizes into hydrogen and OH minus ion. And if it's pure water, you're going to have for every one of these, you have one of those, you're going to have equal amounts of hydrogen ions and OH minus ions. That would be a neutral solution, okay? But in any solution, because it's water-based, you're going to have, whether it's acidic or basic, you're going to have hydrogen ions and OH minus ions. So now when we ask this question, will adding a salt affect the pH? We need to ask, well, whatever I add to the solution, will it have any effect on the H plus or the OH minus ion concentrations? So that's kind of how you're looking at it. Okay, so number one says an anion, you guys, this is all in purple by the way, so write it down. An anion, that's saying the negative ion, that is the conjugate base of a strong acid, will not affect the pH. So that's what it's telling you. For example, so I give you guys an example here. So right here's the strong acid, right? It completely dissociates. Notice it's only got a single arrow going to the right because it completely dissociates. So a lot of these other ones have reversible reaction set. So for example, it's showing it would dissociate into H plus ions and chloride ions. So that's what this is. This is the anion, or the conjugate base of a strong acid. So the question is, would that affect the pH if you added chloride ions? So for example, if I added salt to a solution, right, wouldn't I be providing chloride ions like right here? Well, what does this tell you? It will not affect the pH. And you guys see why? Because here's how you have to look at it. So you look at this negative ion. The question is, what could it possibly react with in the solution that it comes into? When you guys agree as a negative ion, so you're asking, could it possibly affect the H plus or OH minus concentration? Well, you guys think about it. If it were to combine with anything, what would it combine with? The negative ion? Wouldn't it combine with the positive ion? So now you're asking yourself, will those combine and thus affect the H plus ion concentration? The answer is no. Why? Because this is the conjugate base of a strong acid. What do we already know? The HCl completely dissociates. The Cl minus and the H plus ions have very little attraction for each other. So when you put these types of negative ions in solution, it will not readily combine with H plus, and therefore it's not going to affect the concentration. You'd expect to have zero effect on the pH. let's look at another scenario. What about an anion that's the conjugate base of a weak acid? Okay, so let's look at this. So I give you an example of a weak acid. Here's a weak acid. Notice it's not one of the 7. And you know it's an acid, it's got the hydrogen. This is hydrofluoric acid. And you see it's a reversible reaction, so some of it will partially dissociate in this, but in reality, it prefers to be associated like this. So it's going to be going back and forth, but it's heavily favored on the reactant side. Okay? So now let's say, how could I add a fluoride ion to a solution? Well, maybe I could add a salt, sodium fluoride. I put that in solution, and so now that's going to provide fluoride ions. The question is, will that have an effect on the pH? And the answer is yes. Why? So you think about with a fluoride ion, now you think about it. What ion could it potentially interact with? Wouldn't you guys agree the negative ion could potentially interact with the positive hydrogen ion? So the question is, could those potentially combine together? And the answer is yes, because we know it's the conjugate base of a weak acid, right? We already know the weak acid, the reactant side is favored, indicating the hydrogen and the fluoride ion have a relatively strong attraction for each other. They stay together. Therefore, when you put fluoride ions in solution, some of those fluoride ions are going to combine with the H+ ions. And so what's the overall result? Aren't you going to have less hydrogen ions in solution than you had before, right? Because some of them are going to combine with the fluoride ion to form hydrofluoric acid. Therefore, you're going to reduce the H+ ions. So now if you have less H+ ions, what's the effect on the pH? Well, the pH, doesn't it become less acidic? If you have less hydrogen ions, less acidic, the pH increases. So if I was to add this kind of salt into a solution, I would expect a slight increase in pH due to the fact that the negative anion can combine with and reduce the amount of hydrogen ions. Okay, let's look at another scenario. A cation that's the conjugate acid of a weak base will decrease the pH, okay? Cation of the conjugate acid of a weak base. So here's a typical weak base, guys, ammonia, right? So I put ammonia in water. Some of it, right, will combine. But remember, it's a weak base, so the reactant side is favored. But it can attract a hydrogen from water and then form the ammonium ion and then hydroxide. Okay. So now, this is what we're talking about when we say the cation. That is the conjugate acid of the weak base. That's what this is. So let's say I have a salt, like ammonium chloride. I put ammonium chloride in a solution. Will it have an effect on the pH? So what I do is, I look at the cation. What could the cation potentially interact with? Now this time, it could potentially interact with OH- ions. Wouldn't you guys agree opposites attract, right? So then I want to see, could that be a possibility? And indeed, yes it is, because what will happen when ammonium interacts with hydroxide, what's going to happen? You're actually going to, when you agree that this acid will provide a hydrogen and thus to the OH-. So effectively, it's going to reduce the hydroxide ions in the solution. Just imagine you have a solution, however many hydroxide ions. You add ammonium ions, which is the conjugate acid of a weak base. That will combine with that and neutralize it. You can also look at it this way. You guys, this is a weak acid. This is the conjugate acid of the weak base. You guys know that this is acid. It can give up the hydrogen, right? It can give up a hydrogen and go back to NH3. So ultimately, you end up, the way you can look at it is, you're adding an acid. Obviously, what's that going to do? It's going to increase the acidity and lower the pH. Or you could look at it this way. It can combine with the existing hydroxide ions. Therefore, it lowers the amount of hydroxide ions in solution, making it less basic. And if it's less basic, it's more acidic. If it's more acidic, what we would expect is the pH to decrease. Okay, guys, a couple more. I know there's a lot. Let's keep going. Cations of the strong areneous bases will not affect the pH. Okay, so for example, here's a strong base. You guys remember the strong base I said? If you have alkali metals, which are in the first column, or the heavy alkaline earths, if you have them with OH, completely dissociate. Whenever you put them in water, it's very, very strong bases. So they're saying, if you add cations that are the cations of strong bases, you can see this is the cation of a strong base. The question is, would that affect pH? So for example, where could I get like sodium ions? I could just add salt. Once again, but we already know the result. If I add salt, so now I have these positive sodium ions. The question is, what could those possibly react with? Wouldn't you guys agree the positive could? So I'm always seeing which one of these could it affect? Well, a positive ion. So then I'm thinking, could the positive sodium ion combine with the negative hydroxide ion? Well, if it did, but what do we notice? Will that happen? No, because we already see that those together would make a strong base, which completely dissociates the water. There's a very little, if no, attraction between the sodium ions and the hydroxide ions in solution. Therefore, it's not going to have any effect on the hydroxide ion concentration. Therefore, ultimately, it's going to have no effect on the pH. And you guys see that's just confirmed here. We already talked about if we added salt. It's the same thing, but just from the different perspective. Last one. Other metal ions will cause a decrease in pH. So if you guys have metal ions in general, so like for example, let's say we had magnesium chloride, you can see this would be the this would be a metal ion. And you guys know metal ions are cations, right? They tend to lose electrons, they're positive. The metals are positive. So the question is, do positive ions, metal ions, have any effect on the pH of a solution that they're in? So if I added magnesium chloride to a solution, now I have these positive metal ions. The question is, what could it potentially react with? Would it react potentially with H plus ions or OH minus ions? You guys should know it could potentially react with OH minus ions, right? The positive cations with the OH minus ions. And in fact, that is what happens. Some of that magnesium will combine with some of the existing hydroxide ions in solution and form magnesium. In this case, it would form magnesium hydroxide. So those will come together. And so what's the result? What effectively happens when you add these positive metal ions, some of it will in part combine with hydroxide ions, pulling hydroxide ions out of solution. So now all of a sudden you have less hydroxides than you had before. Therefore it makes it less basic. If it's less basic, it's more acidic. And so what you would expect in this case, you would expect the pH to go up. And you guys, these are all different ways that we can manipulate solutions to get certain pHs that we want, because oftentimes that's going to be very key to, you know, an ability for an organism, for example, to survive in aqueous solutions, right? If you're talking, you know, lakes and rivers and oceans and so forth. All right, you guys, we're going to stop there. I know it was a lot. Hopefully you guys can digest it. We'll see you.